And again, the sketch in the text is a little bit better than mine. And so what happens with the capillary tube is they're about 0.03 to 0.05 inches in diameter. So it's very skinny tubing. And what happens is, how long you have the tubing, you're going to have a greater pressure drop. So the longer the capillary tube is, the greater the pressure drop that occurs. So the greater L, greater delta P. And so that's how we size it. And so rather than a valve, which is expensive, regulating this, we have just a capillary tube. So it's a very simple pressure drop mechanism. And I'll draw a sketch, but one of the problems with the capillary tube is we can't have any vapor form in it. It's a little diameter. So you don't want any vapor forming. If you do, that blocks the refrigerant flow. So then you have no refrigeration going on, no refrigerating effect going on effectively. So if we look at this, and we'll start with the evaporator up here. So it's a little upside down, but anyway, it's consistent with the text, so that's always a good thing, I think. So I'll draw this. So this is the evaporator. Going to be here at state 1, going into the evaporator. It leaves at state 2. Again, we'll have this be the ideal vapor compression system. So this is the evaporator. This is inside your refrigerator. So here's your can of water or whatever. So that's where that is, and this is causing the heat flow going in here, evaporating this fluid. Now the fluid coming out is cold, and it's going to go into the compressor, so it goes into the compressor at state 3, out at state 4. Here's the air-cooled condenser. And so typically this is behind your refrigerator or underneath it. This is where you feel warm air coming out. And back, or up. And typically we would see coils, so you'd see these sinuous coils going on. And so now let's draw a TS diagram reflecting this, and then we'll look at what happens. So we have 1, 2, 3. So what happens is, with the evaporator, we're still picking up heat. This is the heat coming in from the refrigerator, the drinking fountain, whatever it is. So this is where our Q in is coming in. But now it's going through, we have this pressure drop. So now this is coming out of the condenser. This is where the capillary tube is. So where I show this bonding, that's where the capillary tube is. So how am I going to prevent, so here I am at, oh, I forgot to do, I have to do one more state here, state 5. So now I'm at state 5, right here. So I'm at state 5, and I need to make sure that no more, that it doesn't flash into a liquid. So I'm going to take the cold refrigerant and keep this a liquid. So I have a cold refrigerant, so I have this 5-to-1 going on, so I keep it a liquid. So the cooling here is going to be the superheating here. How does that happen? I superheat the vapor from 2 to 3, and now I'm going from 3 to 4, and then I cool back down like that. So I have something like that, and I see that H3 minus H2, the mass flow rates are all the same, is equal to H5 minus H1. So the cooling here is the heating here. And what happens is that these are not the most efficient refrigerators, and so if I put in a compressor efficiency, I go up something like that, and it becomes more expensive to run, but it's very inexpensive to build. So for homework in this area, 1625 start. And so this is your home refrigerator, so when you think about it, you often can't see the coils. Sometimes you can see the condenser coils in the back. The coils in the refrigerator are hidden behind panels, so you really don't typically see those, and you have air circulating over them. So now what happens? So this is the home refrigerator. Now what if you were on a ship, which I was, or if you were in a supermarket and you have different refrigerated spaces. You have refrigerated spaces for produce. You have refrigerated spaces for meat that you keep right near freezing. You have refrigerated spaces for ice cream that need to be very cold. And so, do you have a separate refrigeration evaporator for each one, a separate system for each one? The answer is no. And so there's a way for us to have multiple evaporators operating with one compressor. And so let's look at that. And so we'll have our condenser here. It's going to come out, it's going to go down, and we'll have, in this case, 2 evaporators, which will show the let's say we want this at 40 degrees Fahrenheit, and we want this at 0 degrees Fahrenheit. You have the compressor and it goes back. And now let's do the numbering system. So I have 1, 2, 3, 4, 5, 6, and 1. And I haven't connected this yet, but I'm going to connect this in just a second and talk to you about this. So I'm going to have something that goes here because I have to get this refrigerant back. And so, so now let's look at this, what happens. So I have this, and I have the pressure associated with 0 degrees Fahrenheit. So this is a lower pressure than this. So the compressor, to achieve this pressure here, P3, is going to be equal to P2. And that's, the temperature here is 0 degrees Fahrenheit. Let me draw the TS diagram. 1, 2, 6, 7. What's coming out of here is 7. And here is 5. And here is 0 degrees Fahrenheit, 40 degrees Fahrenheit, and whatever the condenser temperature is. So we have that. So what's happening, if I hook this up, I'll erase this. So if I hook this up and just had this pulling here, what would happen is that the suction would be at P3 and it would lower the temperature in this evaporator. If I have this as produce, I don't want the evaporator to be at a low temperature because I'll be pulling moisture from the produce and it'll be freezing on the coils. So I don't want that. I need to maintain this at a higher pressure. So what we have is something called a back pressure regulator. So I put a valve in here, and this is back pressure regulator. And so then coming out of here, what it does is it maintains. Now this is state 7, and this is state 8. I have this craziness going on. So what's happening is, on this side of the back pressure regulator, it can be at this low pressure. It doesn't care. It's going to regulate the pressure here to be at the pressure corresponding to 40 degrees Fahrenheit. So I can control the pressure in here and I don't get that low pressure. And now what happens is this comes in and we have mixing going on here. So I have, in terms of finding my enthalpies, I have a mixing problem going on. And so now at state 2, we're going to have something like this. And we're going to have, and then, so from 7, I have an enthalpy thing going over to 8. So now, so here's state 8. So now I have some refrigerant at 8, some refrigerant at 2. It mixes and will be at state 3. So this will be state 3. And that's the state that we have the compression from, 3 to 4. And so there's example 16.6 in the text. And it's an English unit, so it goes through this, and so you can look at that. What becomes challenging is that finding these values in the table. So finding the enthalpies in the table when you're dealing with fairly nuanced differences becomes challenging. So that you could work on something like this, do a homework problem, 16.16 star. And now I want to look at something called heat pumps. We're not going to look at them in a great deal of detail, but I'll do an example problem with them and discuss heat pumps that we use for heating as well as air conditioning.